Hello and welcome back. Today I will cover RC circuit. As you can see over here, you have a resistor in series with the capacitor, and they're connected to the power supply. Um, what we what we are generating here from the power supply, which is AC source, is a voltage of 1 volt peak to peak, and has a frequency of 20 kilohertz. So one thing I wanted to show at first is this is the AC source signal that we have right now, and based on that frequency, we know that one cycle of this waveform will be 50 microsecond, right? And this is important because the topics that I will cover today is one of them is how to take the voltage reading across resistor and the power supply using your oscilloscope, and the second thing that I'm going to cover is how to measure the phase shift between the waveform for a resistor and the waveform for your voltage source. Ideally, this is what is expected. Once you put down the oscilloscope across the resistor and the voltage source, you should be seeing something like this. So we have the oscilloscope screen where you have the voltage as the y-axis and time in microsecond as the x-axis, and once you plug it in, voltage source will have a waveform like this. Let's call it Vs, and voltage for resistor would be leading voltage source or supply a little bit. Well, that wasn't helpful changing the color, but anyways, this would be VR, and it will be leading Vs. As you can see the difference here, same here. So one of the topics that I'm going to cover is how to measure this phase shift from your oscilloscope, uh, and voltage capacitor for voltage across capacitor would be something like that, let's say, right? So this is what we are expecting out of a circuit like this, where you have the resistor in series with the capacitor and connected to the AC source, and that is giving out 1 volt peak to peak and has a frequency of 20k. And once you measure VR, Vs and Vc, that is how they should look like. So the first topic that I'm going to cover is how to set up oscilloscope across this resistor and across this voltage source so that you can eventually see this waveform. And the second topic I'll cover is how to measure this phase shift or the phase angle or the difference in phase between the waveforms. So let's get to it. I'll be using multi-sim circuit simulation software. I already have the circuit set up over here, as you can see. I'm using a capacitor of 1 nanofarad and a resistor of 20 kilo ohm, and as I said, the signal source is 1 volt peak to peak with a frequency of 20 kilohertz, right? So from the left side over here, left menu over here, we have sidebar, we have the Tektronix oscilloscope. I want to use this because this is basically what we have in in-lab setting instead of the simple oscilloscope that you can use on multisim. So I'm gonna choose Tektronix oscilloscope and put it somewhere over here. So Tektronix oscilloscope has this 4 channels over here, 1 2 3 4, and has a ground to operate. And once you click on it twice, you can see exactly what you usually see in a lab setting. You have the power button over here, and then you have the vertical positioning knob for channel 1 as well as channel 1 menu, and same goes for channel 2, channel 3 and channel 4. And what we usually do, the simplest thing to try is, once you set up your oscilloscope with a probe here, and you connect it to your circuit, and you know that you're receiving some sort of signal or reading in your oscilloscope, we try this auto set button over here, and that kind of calibrates the oscilloscope by itself and then shows you whatever waveform it is picking up, and we get to measure the voltage or the time from the x-axis from that waveform here on this black screen. So I'll keep it on the side. uh, there is something that's slightly different when you are setting up this oscilloscope to measure the voltage across this resistor R2 and the voltage supply V1. Usually what we do is we have this red clip coming out of the channel 1 probe, and we connect that across the, let's actually show you from here, like let's say this is channel 1, and what we do is we connect it across the unit we are trying to measure the voltage, and the ground is usually connected to a common ground either here or put one here, and the ground button is connected like that. So that kind of tells you whatever is being picked up from the capacitor, the voltage reading that you see. So if I run this circuit now, we can use this knob over here at the end to see more cycles and less cycles actually of the waveform. And we are connected with channel 1, so I will use the channel 1 volts per division knob to increase the amplitude. Right, there you go. I want to stop it, so you can use run or stop. Also, let's so this reading kind of right now is telling us what's the voltage across the capacitor, which is okay. This is the usual setup of capacitor, I mean oscilloscope, when you take a voltage reading across a component. But when it comes to this resistor R2 and we do the same kind of setting, that is, I mean, we connect channel 1 from here. This basically voltage reading being taken from at this point basically is the same as taking the voltage reading across the power supply, because voltage drop here uh, is going to be the same as the voltage reading for the voltage supply source, I mean the power supply source. We need to set up the oscilloscope in a way between this V1, the voltage source or the power supply, and the resistor, that we can pick up the voltage reading for the resistor only, also at the same time the voltage reading for the power supply. So this is how I need to rewire it. I'll get rid of this ground, and what I will do is I will have a ground somewhere in between these two components, let's say over here, and then I will have channel 1 hooked up to the negative side of the power supply, because right now my ground is on the positive side of the power supply, and I'm measuring the voltage using this ground as a reference over here. And then I have channel 2 come in and be also on the other side of resistor 2. That way I'm basically measuring the voltage drop across this common ground that is being shared by both the channel 1 and channel 2 of the oscilloscope. And what it does is it's basically taking the voltage reading of R2 and the voltage source in reference to this common ground in the middle. You might as well call it the middle ground. So when I have this kind of setup, and I know from before that I'm expecting a graph like this where VR should lead VS. Let's see what our oscilloscope reading says now. So if I simulate this and I press on auto set over here, it's gonna take a while, and we need to see the waveform properly. So use this last knob on the uh, section per division to span out your signal so that you can see the actual cycles clearly. And right now notice this, channel 1 and 2 is connected, right? And that is different from channel 3 and 4 connection over here. Anytime you have something connected to this oscilloscope, multisim will show you this white, what should I call it, white connections over here to mark that these channels or these pins are being used in the main circuit. So I have channel 1, which is the yellow colored one waveform over here, and I have channel 2, which is the blue colored one over here. And what I need to do is to compare them and see if they're out of phase and if VR is leading VS. Remember from the circuit, channel 1 is connected to the voltage source or the power supply, so that is our VS, which is the yellow waveform, and channel 2 is connected to the resistor, which is the blue waveform. So what I'll first do is I'll stop this so that I can study or analyze the waveform. But before you do that, let's have them aligned on the x-axis of the oscilloscope, which is right in the middle. To change the alignment of the waveform, to change the vertical positioning of your waveforms that you see on the oscilloscope, you can use the position knob for that channel. So channel 1, I will use this position knob to change it and bring it down to the x-axis. You can notice it's written over here in red at the bottom of the screen that channel 1 vertical position is 0 divs. So that means you are exactly aligned with the x-axis of oscilloscope. And to do the same for channel 2, if I look at the channel 2 panel and I use the vertical positioning knob to bring it up and align with the x-axis as well. So now I have my reference, I have the x-axis as a reference to this waveform. It will help me to analyze the signals better. I will change the volts per division and amplify it, not amplify actually, to enlarge the waveform to get a perfect reading. So both channel 1 and channel 2, if you look at the oscilloscope screen at the bottom, it's written 500 millivolt and 500 millivolt, which says that each block or each division in the oscilloscope represents 500 millivolt. So now that being set up, I will span the signal a little bit just to see if VR is really leading. Yeah. So remember, channel 2 was connected to the resistor, which is the blue waveform. I can see that leading the yellow waveform, which is of channel 1 and connected to the power supply. So how do I now measure this phase difference, that they're out of phase, and how do I know how much are they out of phase? That is the second thing that I want to look into. So to do that, first let's look at the circuit, and I mean the waveforms, and see how that calculation goes. So as I said before, we had a signal, a AC signal come in, which was 1 volt peak to peak, and I had a frequency of 20 kilohertz. So the time period for one cycle of the waveform would require 50 microseconds. So we know from this graph over here that if, let's say, this is VR, for VR to complete one whole cycle, it should take 50 microseconds. And let's check if our oscilloscope also says that it takes 50 microseconds. And how do I measure that? So choose any of the waveform, and whichever is convenient. Let's say I wanna go for the yellow one, the channel 1 one, and I wanna see if one cycle of that spans for 50 microseconds. Remember, the x-axis of the oscilloscope represents time, and over here at the bottom of the screen of the oscilloscope, it says m is 10 microseconds. So each block over here represents 10 microseconds. So either we can calculate this, or we can see this visually from here, like how much one cycle, how many blocks one cycle of this waveform spans. It can be 1, 2, 3, 4, 5. I can say from, without measuring, using any cursor or anything, just by looking at it. But to be certain, I will use this cursor button over here to bring in two cursors on the screen and then set them, one at the beginning of the waveform and one at the end of the cycle, so that I can mark the exact time where the cycle started and ended. That way I'll know if it spans through 50 microseconds. So if you press on cursor, this menu for cursor comes up. If you look at the oscilloscope screen on the left side, and it says type off. So I want to change that. I want to take time readings, which is my x-axis. So I want to click on this button right beside to change it to time. And I was going for the yellow waveform, which is channel 1, so my source will be channel 1. So the cursor for channel 1 is now on the screen. You can see it because they are on the left and the rightmost position of the screen. I need to bring them in to a convenient place where I think the cycle started, and the second cursor to a place where I think the cycle ended. To do that, to move the cursors, you have to use channel 1's vertical positioning knob again and keep it moving. As you can see, the cursor perpendicular to the time axis moving. And to me, I think if you look at the yellow waveform, I think it started from here. So wherever the cursor intersects with the yellow waveform is the place where I think that cycle started. And if you look at the menu again, it says cursor 1 is -2 microseconds. Right now it is at -2 microseconds on the waveform. So I am assuming, or from what I see here, I can say that this cycle started at -2 microseconds. Now I'm going to go for the second cursor and move it to a position where I think this cycle ended and record the time reading for that. So select cursor 2, first select here from the menu, and then again use the vertical positioning knob to move it. So as it turns out, for cursor 1 it is the first vertical positioning knob, and for cursor 2 it is the vertical position knob for channel 2. Basically, we are not working on channel 2, but we are using both the vertical positioning knob to move both the cursors. So I think it ended here. As you can see, the second cursor moved a little bit towards right, and that reading over here for cursor 2 says 47.4 microseconds. So cursor 1 is placed at -2.2 microseconds, and cursor 2 is placed at 47.4 microseconds. So that gives me 49.6 microseconds. So I'm a little bit off. Maybe my cursor weren't placed exactly at the end or the start of the cycle, but you can say that this is one cycle which spans through 50 microseconds, and we have the right reading, we have the right waveform, and this is how I can use the cursor on the oscilloscope to take time readings on my waveform and analyze or see how much one cycle spans through, and eventually use those cursors to measure the phase difference. So going back to how I should measure the time difference, the phase difference. So I know that on the oscilloscope screen, 50 microsecond represents one cycle, which means 50 microsecond represents 360 degrees. right? If this is 0 and this is 90 and this is 180 and this is 270, this would be 360, right? So what does one microsecond represent over here, and what does this time difference over here represent? How much angle, right? That would be your theta or phase angle. So phase angle eventually is going to be 360 by 50 times that time difference del t. So this is going to be del t. Sorry about that. This is going to be del t, which is basically the time difference. Let's say this is cursor 2, this is cursor 1. So I need to know what are the time over here. This is t1 and let's say this is t2. So I'll use my cursors to find these two time readings, and you can place the cursors anywhere. It could be measuring this difference, or it could be measuring this difference, whichever is convenient. The idea is to find this del t, which can be later used in this formula over here. Another way of simply expressing this is del t divided by your time period for one cycle times 360. That's the same, and that would give you your theta, your phase angle or phase difference. So if I go back now, I need to find del t from this waveform. So when I'm on the channel yellow waveform, that is channel 1, uh, let's use one of these differences over here. Let's select the cursor again and let's move it to you can either use the peak of the waveforms to measure the difference, or you can measure from the point where they intersect with the x-axis, whichever is easier to locate or identify. And I place it on, yeah. So if you look at the cursor now, it is right on the waveform where it intersects the x-axis, and take the reading for that time. I just moved cursor 1, so on the blue oscilloscope screen I can see on the menu it says cursor 1 is 21.9 microsecond. So keep that reading somewhere written down. I had 21.9 for the yellow waveform in channel 1. Now I need to switch to channel 2 to see exactly the time reading where channel 2 intersects the x-axis, and I'll switch this to channel 2 at first. And now I have the blue cursors over here. I'm gonna move the first cursor again to where I think it intersects the x-axis at that point. Yeah, so the time reading where it intersects the x-axis and the waveform, that cursor reading is for cursor 1 is 18.9 microsecond. So that one, and I had channel 1 set up at 22. So my del t would be my del t would be 22 microsecond minus 18.9 microsecond. That would give me 3.1 microsecond. So when I plug this back into my phase angle formula, I get 3.1 divided by 50 times 360, and that would give me something like 22.3, let's say. So if you perform a theoretical calculation on this phase angle for VR and VS, the voltage source or supply, you will see it would be something like 21.6. That's what if you calculate, and we are getting something like 22.3, which is slightly off, probably because of how we took the time reading using the cursors. It could be little less accurate, but the main idea is if you want to measure the phase angle, the phase difference between VR and the voltage source, you need to see how much the VR waveform is leading the VS waveform, and to do that we are going to use the cursor button on the oscilloscope and place the cursors on the waveforms where it intersects the x-axis, take time readings, and then find the difference of those time readings, and then use that to find the phase angle. I hope that clarifies and that clearly states or demonstrates how this process works. If you have any more question regarding this or how we set up the oscilloscope for this reading, please feel free to leave a comment or reach out to me over my email. To keep this video short, I am not talking about the concepts behind and more details, but definitely feel free to reach out to me if you have further questions on this. Thanks a lot.